Hello everyone. In this video we are going to see how we can combine the PI and PD controllers and obtain a PID controller and lead and lag controllers in order to get the lag-lead compensators. Here we see how they are formed, and then we will learn how to design indeed such controllers, how to tune the parameters of the controllers which are obtained by combining those two controllers. Here we have the definition of the PID controller. The PID controller will have three components of the control action. The first one will be the proportional to the errors through a constant Kp, so that will be the proportional part. Then the second one will be a proportional to the integral of the error through a constant Ki, and the third one will be proportional to the derivative of the error through a constant Kd. So basically we'll have the proportional part, integral part, and derivative part. The PID controller will be a combination of these three parts or three components. And then for the PID controller, we will have the transfer function in this form. So Kp plus Ki over S plus Kd times S. Times E of S will give us the control action in the Laplace domain. Over here again we have the transfer function for the PID controller. It could be also rewritten in this form: Kd times S squared plus Kp over Kd times S plus Ki over Kd over S. And we can see that it has one pole at the origin, a pole at the origin, and there are two zeros, and those two zeros are always chosen as negative real. So this will be indeed the location for the pole and zeros of the controller. Depending on the values that we have for Kp, Kd, and Ki, the location for these zeros will be determined. So we see that this PID controller that we have here is impractical because the system is improper. It has more zeros than the poles. So it's improper, it is not realizable, and we call it as the ideal PID controller. If you want to make it practically realizable, similar to what we did for the PD controllers, we would need to introduce a pole at the point minus PC in order to have the number of the poles equal to the number of the zeros. And that pole will be introduced far from the origin. So it will be indeed somehow similar to what we did for the PD controllers. And then we will have the practical PID controller with this transfer function: K times S plus CC1 times S plus CC2 times S over S times S plus PC. This kind of controller, this kind of practical PID controller will be needed when we want to increase the system type. So we need to improve the steady state behavior significantly by increasing the type of the system. And at the same time, we want to improve some transient behavior. So basically, with the PID controller, we are improving the transient behavior and we are improving the steady state behavior. Both of them could be improved. The PID controllers are quite simple indeed to tune compared to the other available controllers that we have in the industry. PID controllers are quite popular because they are rather simple to tune and they are very effective. And for this reason, majority of the controllers in the industrial plants are from PID controllers. We can also see the PID controller in the form of a series of a PI and a PD controller. Yeah. If you look over here, we have GC of S in the form of K1 times S plus ZC1 over S times K2 times S plus ZC2 over S plus PC. So this part is the PD part, this part is the PI part, and since the transfer functions are multiplied by each other, we can say that we have those two controllers, GC1 and GC2, in series with each other. And this will be equivalent to the GC. And since this is the case, we can design the PID controller in two independent steps using the Root-Locus approach. We can start to design the PI controller first to adjust the steady state behavior, and then a PD controller in order to improve the transient behavior. And instead of PD, if we have in mind the practical one, we will have the lead compensator, yeah? Or we can start by the PD and then design the PI. Both ways would be indeed all right, yeah, in designing the controller. Another thing that we have here is regarding the PI part. If we don't need to increase the type of the system, but we want a very small steady state error without increasing the controller gain, we can remove the integrator and insert a pole close to the imaginary axis. And this is what we were doing with the PI, yeah? From the PI controllers, where we had the pole at the origin, if we were moving the pole towards the left hand side on the real axis, and over there we were obtaining the lag compensator. So with the PI, we had a pole right at the origin and the 0 nearby, and then with the lag we were moving that pole on the real axis towards the negative values, and the 0 would be close to that as well. And in that case we would have the lag compensator, and the practical PID that we had will have this kind of transfer function, which will be referred as the Lag-Lead compensator, because it's composed of two parts. So the first part would be you can think of lag compensator, and the second one would be the lead. And then the design procedure over here would be to design, because they are in series with each other, we can start to design the lead compensator first and then the lag compensator afterwards, or it could be the other way around. So in both cases, designing the PID controller, the practical PID controller, or the lag-lead compensator using the Root-Locus approach could be done in two steps. We will start by designing the proportional controller first, and then introduce let's say a lag or a lead or PD part first to satisfy the transient requirements, and then we can introduce the lag or PI part in order to improve the steady state behavior. And obviously at each step we need to tune the value for the gain of the controller, for the proportional part over here, and check to see whether all the requirements are satisfied or not. So that's how we indeed deal with designing the PID and Lag-Lead compensators. In the next video, we'll go through two case studies in which we will design a Lag-Lead compensator and a PID controller, and you will learn how to find out all the parameters for such controllers. We will do it in the next video. For this video, we are done. Thank you for watching, and see you in the next video.